All right, last time we met, we talked a little bit about chemical reactions, physical reactions. Let's see, I need to adjust this really quick. And we also talked about states of matter. We talked about condensation. And now I want to ask you this question. Well, actually, at first I want to show you this video a little bit more. I showed you this video last time, but I want to have you watch it again. But this time, we're going to look specifically at what's going on right here. Where's it at? There it is. So, tell me, what is it? What's happening right there?
Water.
What's that?
Boiling.
No. The water is what? What's it doing?
Boiling.
It's boiling. That's right. Boiling. Have you ever boiled water on the stove before?
Yeah.
Okay. Where do the bubbles start showing up when you turn on the hot water or turn on the heat? Where do they start showing up?
On the top.
On the what?
Top.
Well, next time you watch, the bubbles eventually come to the top, but they start along the bottom of the pan where the heat is. And the question that I want to ask you is, and I don't want you to answer right away, I want you to think about it. What is it that is in those bubbles? What's in those bubbles? Okay? And that's the question that we have here in our slide. Where's the question at? Okay. When water boils on the stove, what are the bubbles from on the bottom of the container as it boils? Are the bubbles oxygen, hydrogen, water, or accumulated air? Okay.
Is it hydrogen?
That's a good guess. Let's see if we can think about what happens when we heat the water. So if we have a container of water, and we're heating it either with a flame or with a stove, right? This is what's in this container. What's the chemical formula for it?
H2O.
H2O, that's right. H2O. And I would write H2O, but what little sign would I put here? Liquid, that's right. And what do I know happens when I heat water? It goes to H2O what?
Gas.
Gas. So where is that gas? Where's it at? When I heat this and it begins to boil, where's the gas at?
In the bubbles?
That's right. Those bubbles are not hydrogen gas. They're not oxygen gas. They're the liquid that's been converted to the gas. So when we boil and you see bubbles appear, that is from the liquid being converted to the gas. That's a very important thing to know because it's something we do all the time, but sometimes we don't recognize what's actually happening around us. So that is just water in those bubbles. All right, very good. Lots of different examples of chemical and physical reactions. How about this? When you boil water, is that a chemical or a physical reaction? I'll let you look at. That's right, it's a physical reaction. We're not changing the way the water, the hydrogen and oxygen are interacting with each other. All right. now we've talked about some of the properties that we're going to measure. And now let's introduce the units that we use to measure something. In math, if you go and do a math problem, the math problem generally is something like this. 56 times 32. And you get an answer. 27 divided by 3. And then you get an answer, right? 14 plus 200.7, all that divided by 18. And then you get an answer. But you know, nobody ever asks, 14 what? 200.7 what? And divided by 18 what? Right?
Right.
That's math. But in chemistry, every measurement has a unit, always. And so we do a lot of math in chemistry, but we always have to include our units so we know what everybody else is talking about. All right? So for example, if you want to say how tall or how long something is, you could measure it in feet. I'm 5 feet tall. Or meters, I'm 1.2 meters. Or kilograms, I weigh 60 kilograms, right? So these are numbers, but you have to have units so that everybody else knows what you're talking about. If somebody said, I saw the biggest hot dog in the world, this person is saying, I saw the biggest hot dog in the world. It was 203.8. And this person is thinking, I remember seeing a big hot dog at the restaurant down the road. I think I know what he's talking about. Yeah, I saw that hot dog too. It's 203.8. I remember it. It's awesome. What does this person need to say to help the other one know what's going on?
What's the unit?
That's right. 203.8 meters long. That was the longest hot dog at some point. I don't know if there's... Yeah, it is a real hot dog. They might have... I think they cut it up into little pieces and fed it to all these people. But this is a real thing where people don't use units well enough and describe what's going on to their neighbors. In 1999, a while ago now, about 21 years ago, right? NASA lost its $125 million Mars probe because the engineers failed to convert their units. So they thought they knew what units they were using, but they didn't. And the probe crashed into Mars because they were using the wrong units, not because the probe wasn't good enough. So the units kind of are important, right? And you don't want to make $125 million mistakes, right? You have to make sure you're aware of what units you're using. To help us be aware of units, we sometimes can use, they have what are called SI units. SI units. And that means standard international units. So it's the units that people will use internationally when they want to make sure they're using the same units. Now, we don't always use SI units. Initially, they were invented in thinking, oh, everybody will always use these units. But that's not what happened. People still use whatever units they want to. But when things become international, you know which units you can always turn to, or you know which units everybody should know, and that's the standard international ones. So we do want to be a little bit familiar with what the standard international units are. All right? So for length, it's meters. For mass, kilograms. Temperature, Kelvin. That's unfortunate because we either talk about Fahrenheit or Celsius, but it's Kelvin, and we'll have to talk more about that. Time, seconds, okay? So there's other units as well. You can also make new units by multiplying the units together. So, for example, if I have a square and I would like to know what the area of that square is, and it says here that this side of the square is 7 meters and this side is 7 meters, right? These are the lengths of these sides. Do you know how to find the area of that square?
Yeah.
What is the area?
7 times 7 equals 49.
Yeah, 49. But now we can't just say the area is 49. We have to put the units on there. And it's not meters, because what you did is you took 7 meters times 7 meters. So the 7 times 7 equaled the 49, but the meters times the meters equals meters squared. Meters squared. So the answer is 49 meters squared, because we have to, just like we multiplied the number, we have to multiply the units as well. Okay? So you can multiply, divide, add units together, right? So we make sure that we recognize that we can derive, that means do math on and find the units that correspond to the math that we performed. Okay, so we also have ways to describe lengths or masses or whatever unit we are talking about in very large or very small amounts. And that's because if one time I had a conversation with somebody, I said, or what happened was at first he said the particle was 0.000000001 meters long. So I was like, cool. Then he changed his mind and said it was 0.00000000001 meters long. Then I knew his data had problems. If I told somebody that sentence, they wouldn't be able to understand what I was saying because there's too many zeros for them to count as I'm talking, right? Even if it's written out like that, it's just too hard to look back and forth and figure out what the difference is. And so we use, instead of saying that many meters, we use a prefix like nanometers. At first he said the particle was 1 nanometer long, so I was like, cool. Then he changed his mind and said it was 0.01 nanometers long. Then I knew his data had problems. Okay, so this information, 1 nanometer, is easy to digest compared to this, 0.0000000, right? Because I know 1, and this one is 0.01, which is 100 times smaller. All right, so we use these prefixes, and these are the prefixes up here, centa and milli. Have you heard of a centimeter? Have you heard of You've heard of a centimeter, right? A centimeter is about the thickness of your thumb, right? So it's about that long. That's 1 centimeter, right? And now, how many centimeters are there in a meter? Do you know?
100.
That's right. Centa, the prefix centa, is like century. That's right. Centa, like century, or a cent. How many cents are there in a dollar? That's right. There's 100 cents in a dollar. So, the prefix cent means hundreds or hundredths. Centa means hundredths. So 1 centimeter is 1/100th of a meter. 1 centimeter is 1 over 100 meters. Or another way to say that, you could say there are 100 centimeters is equal to 1 meter. All right? So look at all these different prefixes that we have. Centimeter. So have you heard of a millimeter? A millimeter, how small is a millimeter compared to a centimeter? Or how many millimeters are there in a centimeter?
There's 100.
No, it's just 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Remember those little marks on the measuring stick?
Yeah.
Each one of those is a millimeter. 1 millimeter. Okay? Good. So, if I wanted to say 1 centimeter equals how many millimeters? 10. Very good. And what did we say? How many centimeters is equal to 1 meter?
10.
No, a centimeter means 100. So there's 100 centimeters per millimeter, or per meter, right? How about this? How many millimeters per meter?
1,000.
Very good, 1,000. So milli, that prefix means 1,000. And this table here helps us see what the prefixes mean. So there's centa, milli, micro, and that's this many zeros, or 10 to the 6th. 10 to the 6th. Do you know what 10 to the 6th means?
No.
10 to the 6th means 10 times 10 times 10 times 10, and we do that 6 times. That's equal to, that's equal to 10 to the 6th. So, for example, 5 squared is equal to 5 times 5, right?
So 10 to the 6 is 60?
No, it's what's 10 times 10? 100.
600.
Nope. Times 10 is 1,000. Times another 10, 10,000. Times another 10, 100,000. And times another one, 1,000,000.
Oh, it's 6 zeros.
That's right. That's telling you how many zeros there should be. And that's a micrometer. So, how many, and this is the symbol for micrometers, how many micrometers are in 1 meter? 10 to the 6th, which means how many? 1 with how many zeros?
6.
Yes. So what number is that?
1 million.
1 million. So there's 1,000,000 micrometers per meter. Very good. How many, looking at our chart here, I'm going to write it down below here. How many nanometers are in 1 meter? Whoops, that's supposed to be an M. How many nanometers? What's that say there?
1 billion.
That's right. 1 with 9 zeros. 1, 1, 2, 3, 4, 5, 6, 7, 8, 9. Wow, that's a big number. 1 billion nanometers for every meter. Very good. So, this method, 10 to the 12th, 10 to the 9th, 10 to the 6th, 10 to the 3rd, 10 to the minus 6 means we take 1 and we move the decimal place over 6 the other direction. So if I say 10 to the minus 6, I take the number 1 and I move the decimal place that's there over 6 times. 1, 2, 3, 4, 5, 6, and then I fill those in with zeros. Okay? Yeah, if there's a negative 6, you move it this way. If it's 10 to the regular 6, then you take the number 1 and you move the decimal place over 6 times the other way. 1, 2, 3, 4, 5, 6. Right? And that gives you your million. So 10 to the 6th is million. 10 to the minus 6 is 1 millionth. So you need a million of these just to equal 1. Okay? So those are our, what we call our multipliers, or our prefixes. We have centa, milli, micro, and nano, and that's getting smaller. To get bigger, we use, what's that?
You froze?
I froze? So when you're talking about larger values, like a kilometer, a kilometer, kilometer, right? You could say it 2 different ways. Can you see how many meters there are in a kilometer using this table? Kilometer. See the... That's right. There's 1,000 meters in a kilometer, a kilometer. Very good. And we can use the prefix mega, megameters, gigameters, or terameters. So, the ones that we use the most in this class are micro, milli, centa, and kilo. All right, those are the ones that we use the most. And I think from your schooling, you know about centa, you know about milli, so really you just need to kind of learn micro and kilo. And as we do problems, you'll become more familiar with those. So, we're going to look at this slide here and try to figure out how to fill in this table with the missing information. So an example of this, how we're going to do this, is on the right side it says nanogram, and so on the left side we have to describe a nanogram in terms of grams. So it's 10 to the minus 9th grams for every nanogram. What is missing over here for kilograms? How many grams would be in a kilogram?
1,000.
That's right, 1,000. Now, how would you say 1,000 in terms of what we call scientific notation, or using 10 to the something?
10 to the 3.
Very good. 10 to the third. 10 to the third grams is equal to 1 kilogram. Very good. What about this one down here? 10 to the minus 12.
Pico.
Very good. Picogram. That would be 1 picogram. So there's 10 to the minus 12 grams is equal to 1 picogram. How about 10 to, or how about a nanometer? How many meters are in a nanometer?
You froze.
Okay, how many meters in a nanometer?
10 to the 9.
Very good. 10 to the 9th meters, whoops, not 10 to the 9th, but 10 to the what? Very good. 10 to the minus 9 meters for every nanometer. All right, 10 to the 6th grams. What's 10 to the 6th grams?
Mega.
Megagram. Very good. So 10 to the 6 grams is equal to, and you can see on that chart that big M is megagrams. Very good. How about this little symbol? What's that little symbol mean?
Micro.
Very good. Micro, and what's L stand for? Very good. Microliters. So how many liters are in a microliter?
10 to the negative 6.
Very good. 10 to the minus 6 liters in a microliter. Okay, last one. 10 to the ninth. Very good. Hz is called hertz, and that is right. The answer is gigahertz. Very good. So you got all those right. Fabulous job. Okay. Now, it's often important and required for us to convert from, for example, feet to yards, or miles to inches, or inches to meters, or centimeters to inches. And this is kind of a little bit painful initially because we feel like, oh, I have to memorize all these numbers. But we're not going to. We're not going to memorize the numbers. That's what Google is for. We can just say how many inches are in a yard. That's not the hard part. Finding out how many inches in a yard, that's Google's part. Our part is knowing how to use that number to answer the question that we have. So, for example, if I have a length that is, I have a garden that's 7.7 yards long. My garden is 7.7 yards long. And they sell the layering that I want to put on the bottom of the garden in terms of meters. So how long in meters do I need my material to be? So if it's 7.7 yards, how many meters is that? All right. So that is the kind of thing we need to be able to do. Now you can just ask Google how many meters are in a yard, and that's fine. But what we really want to be able to learn how to do is learn how to convert yards to meters by ourselves, because there's some things you can't ask Google. And as we learn to do these practice ones, then later we'll be able to do the more difficult ones. So we're going to practice doing the easy ones first, and then we'll learn how to do the more difficult ones. I don't know. And the answer isn't as important as how we set it up. But do you want to show me how you set that up? Or do you want to talk about that one more? Here's how I would set it up. I'd want to know if I had 7.7 yards. I would draw.
7 times 0.9144.
Okay. So you said that there was, like this says up here, right? 1 yard is 0.9144 meters. So 1 yard is equal to 0.9144 meters. And that's right, because if you multiply how many meters there are per yard times yards, then the yards cancel out on the bottom, and your answer will be in meters. So yes, 7.7 times 0.9144 is the correct way to do that problem. Very good. Very good. Now let's talk more about some different materials that are different sizes, like a penny. You see a penny there is about almost 2 centimeters long. The island of Oahu, right? It is 60 kilometers by 50 kilometers. 60 kilometers long, 50 kilometers tall. This girl is sitting in a box which is 1 meter tall. This hair is 50 micrometers. This is the hair. And then on the hair, you see a nanowire that was made in a chemistry lab that's tied in a knot on that hair. So they can make really small nanowires. This, in terms of volume, this box that the girl's sitting near is 1 cubic meter. This is 3 liters of Coke that boy is drinking. This is an important one. 1 cubic centimeter, which means a box that is 1 centimeter by 1 centimeter by 1 centimeter. That is also identified as 1 milliliter. So centimeters are a length, but if you cube it, you get a volume, and that is equal to 1 milliliter in terms of its volume. So a milliliter is defined as 1 centimeter by 1 centimeter by 1 centimeter. So that's an important one that we'll come back to again later. In the chemistry lab, we have different containers for delivering different volumes. Beakers are not very precise, but they're good for just holding stuff. Graduated cylinders are more precise, but still not as precise as you'd want to make a solution. Whereas volumetric flasks, these ones here, the kind they use in alchemists, right? Those are the ones that you use to make solutions. Erlenmeyer flasks are also like beakers. They just hold solutions. They're not good for measuring volumes. A burette is good at delivering very precise volumes. And you see how it's what we call graduated on the side. When something is graduated, it just means that it's measured. That's why we call this a graduated cylinder, because it has little marks on the side telling you how much volume is in it. Volumetric. What's that?